Can everyone see the whiteboard?
Yes.
Okay. What answers did you get for the first question? Okay, good. 80 meters per minute is right. Ishan, can you explain?
Yeah. So it says Taupe. It's a 50 by 30 meter pool. So yeah. Okay. So Taupe swims back and forth on the long side of the pool, which means he swims 100 meters.
Mm-hmm.
And then her sister Tommy walks around the perimeter of the pool, which is 160. Oh, and yeah, and then by the way, Taupe takes 2 minutes to do 100 meters.
Sounds easy enough.
Yeah, okay. And then Tommy takes 2 minutes to walk 160 meters because the perimeter of the pool is 160. So 160 divided by 2 is 80.
Good. Yep, that's correct. So one extension to this. So what would be the next slowest speed that Tommy could be walking to make this still true, that they meet every time she reaches the end? Any ideas?
$40?
So 40 would be slower than this 80 meters per minute, right? So that would be, it wouldn't be Tommy's slowest possible walking speed, right?
One?
So let's see how that would work. So if basically in 2 minutes, when who was the first, Taupe finishes 100 meters and goes back and forth, Tommy should finish at least one round of the perimeter, right? Now that's what we computed here. The same 2 minutes, she should walk 160 meters and finish one round of the perimeter, right? But really, we don't say that she has to walk one round of the perimeter, right? She has to walk some number of rounds around the perimeter. So what's the next number that she could have actually walked in those 2 minutes instead of 160 meters? Any ideas? So the slowest is 2 minutes, 160. Yep. So otherwise, she could have done 2 rounds around the perimeter in the same 2 minutes, right? And they would still meet when Taupe does back and forth in 2 minutes. So if 2 minutes for 2 times 160 meters is 320 meters. So otherwise, the next would be 160 meters per minute. And so on. You can see you could have done 2, 3, 4 rounds in the same amount of time. But because we want the slowest possible walking speed, it should be the 80. The 40 was kind of the opposite direction. We had to multiply it by 2 instead of divide by 2, corresponding to doing multiple rounds in the same amount of time. Does that make sense? Any questions? Okay, let's go to the second problem. Okay, I see one answer. Are there any other answers? Okay, I don't see many answers. But okay, let's discuss this problem. So there's these two possible moves. I don't know if I can put the image here. Okay, I don't think so. So let's just draw a small picture of the two approaches. So you can do either at each step a reflect or a rotate. So let's draw a triangle here. So one approach is to so one transformation is ABC. If you reflect it, switching the location of the bottom vertices becomes this, ACB. And the other approach is a rotation. So instead of having ABC, we can rotate by one side or 120 degrees. So you get something like this. So these are the two potential transformations. We can do a reflect or rotate. So now we want to see the number of ways that we can return to the original with 5 moves. So in order to do that, let's first start off with if I just had reflects. How many reflects do I need to do before I go back to the original one? Two, good. So I can do a reflect, and clearly that'll switch the bottom two and switch it back, and we reach the original. What about with a rotate? Three times, good. So if I have 3 rotations, I'll reach back the original. Okay, so now so we want a sequence of 5 moves that reaches to the original. So this gives us some ideas. So what are some possible sequences that will reach the original with 5 moves now? So we know 2 reflections or 3 rotations both go back to the original one. So now can we make a sequence of 5 moves that returns the triangle to the original sequence, the original position? Okay, so what would that be?
Reflect, reflect, rotate, rotate, rotate.
Good, yep. So we could do reflect, reflect, and then rotate, rotate, rotate. Anything else?
You could switch it also and do rotate, 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 reflect, reflect.
Good. Okay, so we have a few. So we have 2 combinations now. Now, is there anything other than that? Okay, there's one there. Let's come back to that one. Reflect, rotate, reflect, rotate. Rotate.
Reflect, rotate, rotate, reflect.
Can you repeat that?
Reflect, rotate, 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 reflect.
Good. Okay, so this is an interesting one. So now we reflect the first time, right? So we see like ACB became ABC. Now we do 3 rotations. So we know 3 rotations already brings it back to the original. So we did 1 reflection. The 3 rotations bring it back to whatever it was when we started before the rotations. And then the last reflect puts it back. So basically between the 2 reflections, we do 3 rotations. Okay, so now that we have these 3, is there anything else? Let's see. So we have the 2 reflects next to each other in the beginning and the end. Could they be in any other position? So what about this?
Reflect, rotate, rotate, reflect. Wait.
Okay, so let's see. Let's try this one. Rotate, reflect, reflect, rotate, rotate. So we do 1 rotation. So from this ACB, or originally, we go to BAC. Now we do 2 reflections. So remember that when you do 2 reflections, these effectively cancel each other, right? It's like not doing anything if I do 2 reflections. So rotate, reflect, reflect, cancel, then rotate, rotate again, goes back to the original, right? Now, is there potentially one more like this? Yep, good. So rotate, rotate, reflect, reflect, rotate. Good. So this is again the same idea. We do 2 rotations, then the 2 reflections basically cancel, and then the 3rd rotate. So it's just equivalent to 3 rotations. Okay, so now there's a couple of ones that I see here that mix reflections and rotations. So let's see if that works. So we did 1 rotate. So let's try the rotate, either one. Rotate, reflect, rotate, reflect, rotate. So I'm just going to write the sequence of vertices instead of drawing out the triangles. So let's say it starts off with ABC, or let's read clockwise. So ACB. So think about this first one, ACB. So I'm reading clockwise, ACB. So now let's say the first move. So I think the most recent suggestion is rotate, reflect, rotate, reflect, rotate. Let's try that out. So if we rotate, what do we get first? That becomes BAC. Now reflect. What does that become? BCA, good. Rotate, reflect, rotate, reflect, rotate. Okay, so what is, so after we rotate, what would we next? Good, ABC. Rotate, reflect, rotate, reflect, rotate. So what happens when we reflect here? We get ABC, and the last step, rotate, would give us BAC. So this actually doesn't work. So this is one of the examples where we mix 3 rotations and 2 reflections, but not in contiguously. So here we see that we rotate, reflect, rotate, reflect, rotate, and we didn't actually end up with the original one. So one thing you actually have to be careful of here is that if you have the 2 reflects together, they cancel the operation, and then you can have the 3 rotations wherever. But once you mix them up, in this case, it actually doesn't lead to exactly the same outcome. So you have to be careful here. And so if you try out the ones other than these, you'll see that you actually don't end up with exactly the same starting off. It's actually these 5 are the only ones that work. So you can try out the remaining ones yourself with these rotations to confirm, but this is one example where if you mix up the 3 rotations and 2 reflections, you don't get the same starting sequence. So there's a total of 5 sequences that work. Does this make sense? Any questions on this? Okay, let's move on to the last question. Okay, what were your answers for this question? Okay, good. 2 is right. Dhruv, can you explain?
Okay, so I was looking at the prime numbers. I didn't use any equations.
Can you repeat that? Sorry.
Oh, that was wrong. I don't know how to explain it.
Okay, that's fine. Okay, Ishan, do you want to explain?
Yeah. So I got I got the pairs as 1 and 36 and 289 and 324, which is 1 square and 6 square and 17 square and 18 square.
Good. How did you find those?
I just listed all the squares squares of the numbers and then added 35 to see if any of the 2 matched up.
Okay, good. That's one way of doing it. Any other ways of doing this? Anyone else?
I found 2 prime numbers, so 1 and 6.
Mhm.
And then I added 35 to like 1, and then if it equaled 36.
Good. Yeah, I think that's similar to Ishan's. So another way of doing this is, so you want 2 squares. So in this case, let's say a squared minus b squared to equal to 35. So one nice kind of property in factoring that you can do is this a squared minus b squared, you can factor it as a plus b times a minus b. So what this tells us, if I know the 2 numbers that I take the squares of and their difference is 35, if I add them and if I subtract them and take the product of those 2, that has to be 35. So then I just need to find ways of dividing 35 into 2 as the product of 2 numbers, that one is the sum of the 2 and one is the difference. So it could be 7 or 5, could be 35 and 1. So these are the only 2. So we need the sum to be more than the difference. And then we want 2 integers here. So if the sum is 7 and the difference is 5, what should the 2 numbers be? This should just be 6 and 1. And if the numbers are 35 and 1, for the sum is 35 and the difference is 1, the numbers should be 18 and 17. And then we can confirm this, that 6 squared minus 1 squared is 35. And then 18 squared minus 17 squared is 324 minus 289, which is also 35. So if you're given any that the sum of, or that two's perfect squares differ by some number, you can write it as a squared minus b squared is that number. So a plus b times a minus b should be that number. And then if you find two factors of that, you can set one to be a plus b, one to be a minus b, and then find out what the two numbers should be with that sum and that difference. Any questions on this? Okay, then that's it for today. We'll see you all next week.
Thank you.
Thank you.
You're welcome.